The world we live in is composed of matter and energy, which turns in the form of heat while transferred to matters. According to a great man named Einstein, they're interchangeable. The matters in the sun trigger nuclear fusion and give out heat to us on Earth. Campers burn ooze to boil the water. We eat food to keep our body warm. The transfer of heat is involved in almost every aspect of life, so today I'm going to mainly talk about the energy within the matters and how they transfer. Firstly, when the energy is transferred between substances in the form of heat, usually from the hotter one to the colder one, physical changes may occur in many occasions. For example, when a red heated metal ball is dropped onto a huge block of ice, the ice melts or even sublimates while the metal loses its red color. In the microscale, the bonds between water molecules are broken by the heat so that they lose their solid shape and transform into liquid or vapor. As we're learning you need to do work to move an object. Similarly, to break the intermolecular force, which is essentially the electrostatic force, the input of energy is necessary. One thing we should notice is that when a substance, like water, changes phases, it takes in or gives off heat without changing the temperature because the energy in or out is used to break or form bonds instead of increasing the movement of molecules. For example, we use an immersion heater to heat up a cup of water with ice at a temperature remained at 1 degree Celsius at the first 20 seconds and 104 degrees Celsius in the last 10 seconds. Although the heater continuously putting energy into the water or ice. Within those two time periods, the ice melted and the water vaporized respectively. The temperature would also remain the same when the water vapor condenses and the water freezes to ice. To calculate the energy needed to change the phase of certain substance, we need to use a formula Q equals mL, in which m is the mass and L is the latent heat for specific substances in specific transitions, between solid or liquid or between liquid and vapor. Secondly, when two components of system have different temperatures, the energy from the one with higher temperature tends to transfer to the one with lower temperature. The concept of temperature is essentially the amount of kinetic energy in substance. Thus, the heat transfer is in fact the process of averaging the distribution of kinetic energy within the system. The end of this process is called thermal equilibrium, in which objects have the same temperature and the same kinetic energy. In the lab, we heated two pieces of metal to 100 degrees Celsius and put them into 2 cups of water with a temperature of 20 degrees Celsius. The metal and the water reached 32 and 34 degrees Celsius respectively. Why is not the average of the temperatures of the water and the hot metal? This relates to the formula for heat transfer, Q equals mc delta T. Because the water and the piece of metal have different mass and specific heat capacity, the changing temperature are not the same, since the transfer heat is the same for both objects. According to the conservation of energy, the total energy in the closed system should remain the same. In other words, the energy given out by the metal should equal the energy received by the water. Caution, this formula doesn't work when objects are changing phases, since delta T remains 0 during phase transitions. Thirdly, not only substances transfer energy, the reactions do too. Reactants react with each other and form new products. In microscale, the bonds between the molecules of reactants broke and new bonds formed between different combinations of molecules which form the product. As I mentioned in the first part, breaking bonds require energy input, while the formation of bonds require energy output. Thus, if the heat input needed to break the bonds within the reactants exceeds the heat output needed to form new bonds for the product, reaction is endothermic because the overall process takes in heat. In the opposite situation, the reaction is exothermic because the overall process gives out heat. To compare the heat input and output, we need to use the formula delta H reaction equals sigma delta HF product minus sigma delta HF reactants. HF stands for standard enthalpy for formation for any substance, which is how much heat is required to break or form bonds for 1 mole of a specific chemical. For example, the energy needed to add in to break 2 moles of ethanol and 3 moles of oxygen is 478.4 kilojoules, while the energy needed to give out from 4 moles of water and 2 moles of carbon dioxide is 1,757.3 kilojoules. Since the reaction gives out more heat than it takes in from the surrounding environment, the burning of ethanol is exothermic, and that's why we use ethanol as an efficient fuel. Lastly, the triggering factors of reactions closely correlates to the heat. There are 2 major triggering factors, negative delta H reaction and positive delta S, the increase of the number of molecules. Since the matters with high potential energy are less stable than those with low potential energy, the reactants tend to give away their potential energy in the form of heat. Therefore, in the case of exothermic reactions, the release of energy is the main factor. For the endothermic reactions, the increase of entropy can be the triggering factor. According to the second law of thermodynamics, the entropy of the universe never decreases. In other words, reactions tend to transform into a more disordered combination of molecules, and they usually accomplish that by breaking into more molecules. In conclusion, when delta H reaction is negative and delta S is positive, the reaction always happens. When delta H reaction is positive and delta S is negative, the reactions never happen. When delta H reaction and delta S are both negative or positive, the reactions sometimes happen. To determine whether the reaction is going to happen or whether it is spontaneous, we need to use a Gibbs free energy. The formula is delta G equals delta H reaction minus temperature times delta S. Gibbs free energy is negative, the reaction is spontaneous. When it is positive, the reaction is non-spontaneous. As we can see, the heat is not only a major subject in physics and chemistry, but also an essential component of our daily lives. To understand thermodynamics can help us know more about the driving force of the world and the direction to which the universe is heading.